So we are discussing periodic classification. I would like to remind you, and as many times as possible regarding this periodic classification. It's not trivial, it is so serious, it stimulates research. These are all the things which I would like to tell you whenever I go for a subtopic. Please understand that it's not about placing them in rows and columns. As I told you, you have infinite number of shells in an atom, and each shell is regarded as a period. Each period is regarded as what? Shell. And as you know, shells are designated with principal quantum number, and the number varies from 1 to infinity. So you can expect infinite number of what? Shells. That means infinite number of what? Periods, indicating that even though we have the seventh period itself is what? Incomplete. If you actually take the long form of periodic table proposed by Moseley, where you have 7 periods and 18 groups, right? So the periodic table itself is incomplete, and the seventh period itself is incomplete. So it leaves a scope for you and me, go out, venture out, discover an element. I have a position for you in the periodic table. It's as simple as that. So it's basically leaving you scope for the research. That's why I say it stimulates what? Research for you. The other aspect which everyone must understand is, the fundamental thing. If someone is asking you what is the basic difference between the 120 odd elements that are placed in the periodic table, what is the basic difference? You can have n number of differences, but I think the basic difference would boil down to atomic radii, right? So atomic radii is the fundamental thing on which the mode of activity of a particular element is depending upon. When I say mode of activity, I am referring to their physical and chemical properties. That's why even the modern periodic law says the physical and chemical properties of elements are functions of atomic radii. So that's why in the first place we have discussed atomic radii, and then following it up with what? Periodic properties. A property that repeats itself at regular intervals. After all, we have decorum in the periodic table. We don't have randomness, because the periodic table classification or the framing of the mainframe of the periodic table is done through schemes, principles, rules. It's not a random way. So you can expect some properties repeating themselves at regular intervals, and those are called periodic properties. And what is common in all this is, even though we define in a different way, but ultimately they are all functions of atomic radii. They are all functions of atomic radii. So if simple question is asked to you, what is the basic difference between 100 and odd 20 elements odd in the periodic table? Well, I can simply say very casually, it's nothing but what? Atomic radii. Lithium is behaving as lithium with its own set of properties because of its size, and cesium will behave in a different mode of activity because of its size, or any other element. You must understand this. Right? So non-metallic properties because of their size, metallic properties because of their size, and in between metallic and non-metallic, if you have certain such mode of activities, again this is because of what? Mode of activity. You must understand that. So basically that's why the periodic properties are functions of what? Atomic radii. And if you remember, when we start off with atomic radii, then I was telling you about what? Electropositivity, electronegativity, electron affinity, and we are discussing ionization potential. Well, in today's session also, I think we'll get into the ionization potential and its applications. Don't forget the scheme in which what we are doing. What we are doing is first define a periodic property, frame a function. When I say frame a function, investigate on what factors does that depend. The second thing what you are supposed to do is then go for the trend. Now, going for the trend implies how does it vary in a period, how does it vary in a group, and then finally go for its applications. When I say applications, I'm actually referring to the questions that are asked in the exam. That's what I'm actually referring to, right? So, in that process, let's go in for ionization potential and its what? Applications. Let us do that. Remember even that electropositivity and ionization potential and reducing power, right? I would like to list it out for you. Ionization potential, electropositivity, and reducing power. These are all the three things which we speak for metals, right? Electronegativity, electron affinity, and oxidizing power. These three are the things which we'll be discussing for non-metals, which are placed to the right of the periodic table. Good metals are placed to the extreme left of the periodic table. For them, we speak in terms of what? Electropositivity, ionization potential, and what? Reducing power. and of course metallic character, because metallic character will be showing all these three which I was telling you, right? So let's define first as according to the scheme. Let me define it. What is ionization potential? If you look into this, ionization potential is basically energy required. It's basically energy required. It's not it's not given out. It's required. Well, if you look into the word, you call it to be ionization energy, or I call it to be ionization potential. But remember, why potential? Because remember, we are trying to remove an electron from the clutch of the nucleus. And that will happen. We need to spend the energy for the simple reason I brought the electron from infinity, from some point in the infinity, and brought it to the clutch of the nucleus. And when I'm doing so, I'm actually vomited energy. I have done some work, and that work is referred to be an ionization potential. The amount of work which I spent in bringing an electron from an infinity to a particular point under the influence of the nucleus, well, I lost energy. That much energy, you need to spend it out to remove it, right? And the potential is nothing but the work done in bringing charges from infinity to a particular point. So it's also referred to be as ionization potential. Synonymously, you can also call ionization energies. So it's basically energy required. It's never what released. Ionization energy is basically energy required. To remove or to extricate, I can say to extricate electrons from the outermost shell. Outermost shell. I would like to underline outermost shell. Remember that in chemistry, as a practice as a chemist, I always underline outermost shell. For the simple reason, only the outermost electrons will be participate in bonding. Not every electron will participate in bonding under normal conditions. Yes, of course, you might ask me a question, why only outermost shell electrons? Do the inner electrons can't be removed? You can say, yes, they can be removed, but not under normal conditions. But remember that an atom can be stripped absolutely naked. The atom can be stripped absolutely naked, leaving the positive charge, which is, we call it to be plasma, but that will not happen under normal conditions in which the chemistry is defined. But remember that, yes, of course, you can strip the atom naked, and that will be happening at 10 power 6 Kelvin, a million degrees Kelvin. You must understand, and chemistry doesn't happen, normal chemistry doesn't happen at that temperatures. So if the question is, why only outermost shell? Because outermost shell electrons only participate in what? Bonding. They only get redistributed and they invest in bonds. You must understand that. So the energy required to extricate an electron from the outermost shell, of a neutral gaseous atom. Well, I would like to underline neutral gaseous atom. Remember this. Energy required to extricate. Extricate is nothing but removal, right? So to extricate electron from the outermost shell, that's important. You're not doing it from the center or the first shell or something like that. Outermost shell has significance, so I need to remove it from the outermost shell, right? Once the outermost shell is finished, then I think the atom will shrink, and then if possible, which is not possible, yes, if possible, then we'll go for the next shell, but otherwise it's mostly what? Outermost shell of an atom. Of which atom? Of a neutral gaseous atom, right? Neutral gaseous atom means basically what you're doing is you're removing the electron. So this ionization potential, this removal or this extrication of electron is basically happening in a gaseous state of the atom, rather neutral gaseous state of the atom. The atom must not be charged. The atom must not be charged. It must be neutral. Of course, atoms are neutral. The atoms are neutral because the number of positives are in equilibrium with the negatives. And in such equilibrium, you convert that into a gaseous state and then try to remove an electron. That's called an ionization potential. And that's what is energy required. That's what he is telling, right? So let's say this. And as I told you, ionization potential is basically told for metals. So let's indicate the metal atom to be M, right? And this is a neutral metal atom. Mind you, this is neutral. Neutral in the sense, there are two conditions for an atom to be neutral. The number of positives must be equal to number of negatives, but that is basically an essential condition. but sometimes number of positives equal to sometimes negative, the number of negatives, but still you can't expect the atom to be neutral. The only thing is you should say in a proper way that the positive charge distribution is in equilibrium with the negative charge. Then that's when we say the atom is what? Neutral. Right? So that neutral atom, what you do is you remove an electron, you spend some energy, and that's called I1, and this is called the first ionization potential. First ionization potential. Mind you this. Now remember, before going here, as I told you, we need to convert this into a neutral gaseous atom. So what you're supposed to do is you need to convert this into a gas. So that's what is the neutral gaseous atom. And for this, you need to spend some energy, and that's what is called sublimation energy. Remember that. It's basically called sublimation energy. You must understand this. It's a sublimation energy. Sublimation energy is the energy required to straightaway convert the solid state atom to a gaseous state atom. You must understand. So if you look into this, the neutral atom is first being converted to the neutral gaseous atom. That's what it's telling. For that, energy is required, and I call this to be sublimation energy. And one hint which I can drop it for you, if you're taking the case of alkali metals, if you take the case of alkali metals, then understand that the sublimation energies of all alkali metals is same. Strange. Well, remember that the sublimation energies of all the alkali metals is absolutely same. Right? So if that is a question, remember that. And you know, if you are actually comparing any of the properties within the alkali metals, and if sublimation is one of the factors, remember that the sublimation is not a differential factor for any property of the alkali metals, because there is absolutely nothing to differentiate in alkali metals, because the sublimation energies are basically same for all the alkali metals. You must understand that, right? So it's a neutral gaseous atom is ready for you now. This neutral gaseous atom now, this neutral gaseous atom is now ready for removal of the electron, M plus E, and this is I1. This is basically called the first ionization potential, and then you are removing it from the clutch of the nucleus. So that I1 is the energy which you have given it to remove the electron from the clutch of the nucleus. That's called what? Ionization potential. That is a definition. So normally what students do is they just think that, you know, the electron is removed from the outermost shell. They're removed from the atom. No, it's not like that. You should be very carefully observing, very closely observing the definitions, because you have a lot of factors in that. And one of the factors is basically, remember that it's energy required, it's never absorbed. Remember that it's energy required, it's not never released, right? And it must be done from the outermost shell of a neutral gaseous atom. And for making a neutral gaseous atom, I think you have to sublimate it and then try to remove the electron from the clutch of the nucleus. That is the definition. Now, once you define, it's time for going in for investigating on what factors that ionization potential depend upon. Well, it's a clear thing. Well, I would like to write it, framing a function for ionization potential, and it is like this. And observe here, right? Outermost shell far away from the nucleus. I think the amount of energy we are putting in will be lesser. It's only a common sense, right? So extrication would be easier for you when the outermost shells are basically far away from the nucleus. You must understand that, right? If that is the case, then remember, if that is the case, then I clearly understand that ionization potential is basically a function of size again. Now remember, that's why, you know, you quote any periodic property, ultimately it's boiling down to size. So that's why even the modern periodic table is basically telling you the physical and chemical properties of an element is basically a function of atomic sizes. So any property exhibited by all the elements in the periodic table, if someone is asking you why, at any point of discussion in your life, then it will be just boiling down to size and nothing else. It's absolutely nothing else. So even the modern periodic table law is based on what? The sizes. So this is no difference. The ionization potential again is a function of size. Electropositivity was a function of size. Electron negativity was a function of size, electron affinity was a function of size, and even ionization potential is of course what? A function of size, and it will be a function of size. If you wanted an exact relation, then understand that ionization potential is basically inversely related to size. It's basically inversely related to what? Size, you must understand. If that is the case, then understand that in periods, the size decreases, then ionization potential must increase. Right? The ionization potential must increase. So from left to right, the size is decreasing, so the IP must be what? Increasing, you must understand. And then in groups, right, the size basically decreases, so you can expect ionization potential being what? Decreasing. That's how the trend is. We are following a scheme. First you define the periodic property, then you write on what factors that is depend, that's nothing but size here, and how does it vary in the periodic table is nothing but you can actually see the size decreases in a period, so ionization potential must increase, and the size basically, in group size, size actually increases, so ionization potential basically what? Decreases, you must understand. So in a period, size decreases, IP is increasing. In a group, size is increasing, so ionization potential would be what? Lesser, you must understand that, right? If this is the case, then it's time for going in for what? Applications of ionization potential. So what are all the things which are extremely important? One by one we will discuss. And this one is basically linked to your exam. Each one which I will be discussing now, I'm actually basically linking it to exam, and you can bank on these questions. You can basically bank on these questions for sure. These are the questions which will be coming in the exam. Let's go in for applications, right? Right. Observe carefully here. The very first one. The very first applications of ionization potential. The applications of ionization potential. Well, I would like to introduce a term also here, and I want the attention of everyone. And remember, you have 18 groups in the periodic table. I draw the attention, please, because you can actually bank on these questions for the exam, right? You have 18 groups in the modern periodic law, right? A modern periodic table. So in the 18 groups, one thing is very much visible and obvious and distinct. Well, I would like to write the statement for you. Then once I write it, then it's time for reasoning that statement, right? And once you reason that statement, that forms a question in the exam rather, right? So let me write that statement. What I'm writing, you have 18 groups in the periodic table. You have something very obvious, distinct and clear observation in all the 18 groups in the periodic table. What is that? Let us see. Let me write that. Look into this. Look into this. The first three elements, the first few elements, the top few, rather I would like to call this to be the top elements behave differently. When I say behave differently, and when we are dealing with chemistry, this behavior is something related to the mode of activity. When I say mode of activity, I'm referring to their properties, their physical and chemical properties, that's all, right? That is the behavior, that I'm referring to a chemical behavior, right? In all the 18 groups, not only here, in all the 18 groups which you have in the modern periodic table, the top elements behave differently from the bottom ones. From the bottom ones, you can actually see here, right? The top ones have a different, clear, obvious properties, and the last three elements will be having almost similar properties. Well, I would like to say, I think the first few elements, or the top elements have clear properties, have clear mode of activity. Clear mode of activity compared to bottom elements. compared to bottom elements. You must understand. Now, what do you mean by this? What do you mean by this? Let's take a group and analyze this statement if you're actually not able to follow this statement. Well, I would like to spend some time here till you follow, right? So observe here what I'm telling is in all the 18 groups in the periodic table, the first 3 elements, the first 3 or 4 elements, the properties can be distinguished. You can say that lithium completely behaves from the first element will behave differently from the remaining elements. The second element also behaves differently from the remaining elements. The third element also behaves differently from the remaining elements. But the last 3 elements almost behave similar to one another. Almost behave similar to one another. That's what I meant by it. That's what I meant. The top elements have a clear mode of activity compared to the bottom elements, which show some similarity between them. Well, if I can give you a specific example for this, then observe here, if I can take the first group, example. If you look into this example, take the case of the first group elements. This I'm referring to the alkali metals. The alkali metals which are placed to the extreme left of the periodic table. And if you look into these alkali metals, this one is actually reflected here. Look into this. If you say lithium, you have sodium, you have potassium, you have rubidium and cesium. What is observed here, right? These three actually have almost similar properties, almost what? Similar properties, similar periodic properties or electropositivity or whatever. You can't, there is absolutely not much to differentiate in this property. Of course, they have their own identities. I'm not denying it. But I think there is absolutely not much to differentiate when the way the first and the second are behaving compared to the remaining. Lithium, if you see, even though we call this to be alkali metals, the best metals in the periodic table, to tell you, lithium behaves completely different from the remaining elements. Like lithium will be forming complexes. And lithium, most of the compounds are covalent also. So lithium does form covalent compounds. Yes, right? It forms covalent compounds. It behaves differently. It forms complexes. Whereas sodium has its clear, distinct, obvious properties. Obvious, right? And if you look into the reactivity, even in the first group, reactivity of these first groups, lithium, if you drop it in water, it doesn't react on its own. You have to heat it, rather. And the sodium, when you drop it, I think it vigorously reacts. And potassium, rubidium, and cesium, yes, they are violent towards water, and the degree of violence exhibited by potassium, rubidium, and cesium is almost the same. So understand what I'm telling. You have 18 groups in the periodic table, and in all the 18 groups, the first one behaves differently, the second one behaves differently, the third one is also behaving differently, but the last 3 elements in a particular group, the properties are not so differentiable. That's what is my problem. That's what I'm trying to explain this to you, right? So why such a thing is happening? That is the question. We need to reason that. Why such a thing is happening? Well, as I told you, lithium forms what? Covalent compounds. It is seen in what? Complexes. The vigorosity with which the lithium reacts with water is absolutely subtle. It doesn't react great way. We have to push lithium to react with what? Water. Whereas sodium, when dropped in water, yes, it does react violently. And the violence increases down the group, but the degree of violence exhibited by the last 3 elements is clearly distinguishable compared to what? Sodium, and much compared to what? Lithium, right? So why such a thing is happening, and this is a question which is asked in exam. Let me put the assertion first, and then we'll go for the reasoning, right? Let me put the assertion. This is the explanation what is giving. Let me put a proper statement, and then we will see. Observe carefully here. Now, by this time, if you are intelligent enough, then I am telling you that the properties of the first few elements compared to the last few elements are completely different, and the last three elements you don't have any property so much differentiable. If I'm asking, if this is the question, so the obvious question a student must be thinking, who have been listening to me from quite some time in periodic table, then the obvious, I told you that any question which is asked in chemistry, any question that is asked in chemistry, whatever the discrepancy, any question that is asked in chemistry must be boiling down to size. At least if you don't know the details of anything, if any question is asked, I think you should say at least the sizes are varying, so hence the properties are varying and differentiable. And if you are unable to distinguish any properties of a particular element, they look similar, then I think the obvious thing is the sizes are same. Then the sizes are same. You can simply say, right? So if I say the lithium is showing something different properties, its size is completely different compared to sodium. And when I come down to potassium, rubidium, cesium, I think the sizes are also similar. That's why they show similar properties. Similar properties. Right? It will boil down to only one thing, that is atomic radii. It's as simple as that. Right? So any question which is asked in chemistry should be a function of what? Size. So let me write that statement for you for a better understanding. Watch carefully here. Watch carefully here. So I write this, even though, understand please, even though size increases in a group, even though the size increases in a group, the truth is, in any group, the size will be increasing. The size will be increasing. In any group, the size will increase. That's an obvious thing, you know very well. That is how the trend of atomic size is in a group. But I say something else. Even though the size increases in a group, the magnitude of increase decreases down the group. Decreases down the group. You must understand. Even though the size increases down the group, the magnitude of the increase of size basically decreases down the group. You must understand. Now, what do you mean by this? What do you mean by this? So, I would like to explain this. Watch carefully here. What I mean. Take the case of first group. The first group, take the case of first group, and it is lithium. This is the statement, this is the assertion what I am making. What is the assertion? Even though the size increases in a group, understand carefully, the assertion, if you don't understand, there is no point in reasoning, right? So I draw the attention of everyone. So even though the size increases in a group, that is the truth that the size increases in a group, right? But the magnitude of increase down the group, right? The magnitude of increase basically decreases down the group. There is an English confusion here. What I mean is, when you move from top to bottom, you find an increase in what? The size from the first to second, second to third. But from third onwards, if you actually see, the magnitude of increase from the third element onwards basically decreases. If I can give you an arbitrary values, these are not actual values. These are absolutely not actual values. These are not actual values. Some arbitrary values for your understanding, I am giving it to you. Watch carefully here. This is lithium. This is sodium. This is potassium. This is rubidium. And this is cesium. Assume this. I am explaining this statement to you here. And the values which I am putting it here is only arbitrary for your explanation. Right? If you want to receive the real values, take a Clark table, take your textbook, refer the sizes of lithium, sodium, potassium, rubidium and cesium, and you can understand the trend. Right? You need not remember those values. Arbitrarily, if I give this to be, say, 100 angstroms, assume that's 100 angstrom size, angstroms, size, right? That's what I'm telling. The size increases in a group, right? But the magnitude basically decreases. Suppose if it is 100. And here you find a jump of 150 angstroms. Wow, good. 100 to 150 you can distinguish. There is a 50 increase jump. Fine, it's jump, and you should not be surprised. And even I'm not surprised. Because down the group, of course, what the size increases, and it's a clear jump. I call this to be a jump because you have a 50 units jump here. Potassium, okay, 221 angstroms. Wow, there is a difference. So you are actually differentiating. There is some units differentiation you can actually see here. 50 units to the top. For the second, you have around 70 units increase, and I'm not surprised. I'm not surprised because our teachers told me that from top to bottom, I think the size will increase. That's what is happening here. You can see the size is increasing. But the issue is, I'm drawing your attention. But the issue is, what is the issue? The issue is basically this. Watch from now. Here, I'm not surprised. Here, I'm not surprised. Look at the magnitude of increase. This is 50. And look into the magnitude of increase, approximately 70 angstroms. And now comes the issue. For rubidium, it is basically 221.5 angstroms. Come on. This is 221 and this is 221.5. Purely arbitrary. These are not actual values. These are not actual values. If you want actual values, please refer a Clark table or your textbooks. The values are given. Now what is happening here is you have 50 units magnitude increase here is 70, and then suddenly there is 221.5. This is around 0.5 angstroms increase. 0.5 angstrom is increase. Well, I'm sticking to the statement. I know teachers were telling me in a group the size will be increasing. Yes, true. They told me truth. Yes, the size is increasing, but the issue is the magnitude of increase which you see it on the top of the elements, you don't see it at the bottom. You don't see that in the bottom. And if you go to the next element, it is somewhat, it comes to around like this. Don't find much difference, somewhat like this. Those are an arbitrary value. Don't look into the values. Look into the trend. Don't look into the values, just look into the trend. This is increasing by 50, 70, 0.5, and then there is further increase. The size is increasing, but the magnitude of increase basically is decreasing. You must understand. And you can't put it this way, 226 point, right? This will be, 221.53. There is an increase. There is an increase. But the magnitude of increase is basically what? Decreasing. Well, if this is the case, we have modern periodic law which says that the physical and chemical properties of an element are functions of atomic radii. In fact, the mode of activity of all the elements in the periodic table depends on size. Well, I'm not surprised if lithium behaves differently than sodium, because the difference in sizes is 50. There is a clear difference in mode of activity of the first element with the second element. And also further clarity, distinction, distinct features you will find between sodium and potassium because the increase in 70 angstroms increase. But I think the properties of rubidium and cesium would be similar because the size is also same. Potassium, rubidium, cesium, the sizes are basically same. You must understand. So you have that closeness of mode of activity between at the bottom where the sizes are what? Similar. That's what is the assertion which I'm making. That's what I meant by this. Even though the size increases in a group, the magnitude of increase decreases down the group. That is shown through an arbitrary values. These are not actual values. If you want actual values, please get through a book. This is what is a trend which is followed. Now the question arises, if you followed the assertion, then the question arises, why this variance? Why this variance? Why the size is, magnitude of increase is higher on the top and that magnitude is basically decreasing down the group? I think we need to reason that. We need to answer that. That's the assertion. Let's go in and check out what is the reason for such a thing. Shall we? Yes. Watch carefully here. If you see, one of the major factors, I draw the attention of everyone. One of the major factors that influence, right? One of the major factors that influence, right, sizes is, and I write it here, observe carefully here, it is basically shielding effect. It is basically shielding effect, or sometimes even called screening effect. It's basically nothing but what? It's also called screening effect or shielding effect. Now, what is this shielding effect? Let us understand here. Let's understand here, right? Now, you have a nucleus, and between outermost shell and the nucleus, you have several shells in between. And remember, we are matured in science, and I was always telling you, shell is no different from electron. Electrons itself are shells. So, otherwise also I can say, between the nucleus and the outermost shell, the number of shells increase. I mean also the number of electrons increase. The number of electrons also increase. Right? So between nucleus and the outermost shell, I write it rather. What is screening effect? What is screening effect? I would like to write this. Between nucleus and outermost shell. Between nucleus and the outermost shell. Well, I say shell, I am referring to an electron because both are synonymous. No electron, no shell. Without electrons, you have shell as a permanent rods, you are mistaken. No. Electron itself is shell. Synonymously, you should think it. Right? So, between nucleus and the outermost shell, between nucleus and the outermost shell, if the number of shells increase, number of shells, I'm referring to again what? Electrons. Number of shells increase. Right? Between nucleus and the outermost shell, if the number of shells increase, then, look into the consequence. Then the consequence of such a thing, which you can't ignore, you can't discount. If it is a small thing, we would have discounted it. If it is a small thing, we would have discounted it. Right? So, between the nucleus and the outermost shell, if the number of shells increase, then, look into this. Effective, not effective, it is effective, not effective. Affection is love, this is effective. Effective means resultant. Effective means the resultant, the consequence or the resultant. Right? So, between the nucleus and the outermost shell, if the number of shells increase, then the effective nuclear force of attraction, the effective nuclear force of attraction. Sometimes people are lazy or out of ignorance. You can't be, sometimes people are lazy or sometimes people with ignorance, what they do, right? They don't write nuclear force of attraction and cut short the statement as nuclear force. If I am the paper corrector or the examiner, then I would like to give you 0. So understand, never replace a nuclear force with nuclear force of attraction. There is difference. You cannot be lazy all times. You must write the complete statement as I am writing. I would have stopped it here as nuclear force. There is difference. Nuclear force and nuclear force of attraction. There is difference. Nuclear force exists within the nucleus. It's a short range force. It's a short range force. Those forces exist in subatomic state. That is, within the atom you have the nuclear part, within the nucleus you have the nuclear force. And nuclear force of attraction is in the extranuclear part. That is between the nucleus and the electron. There is difference. So you can't be lazy. You can't be lazy and while talking to your friend, you can't say that's nuclear force, this is nuclear force. No, absolutely not. It's not nuclear force. The force that exists between nucleus and an electron is an extranuclear part force. That's called nuclear force of attraction. Nuclear force is done which is within the nucleus, and this is called what? Short range force. There is difference. Don't ever substitute one for the other. And don't be lazy, right? And the issue is then effective nuclear force of attraction. Effective is what? I call this to be resultant. The resultant nuclear force of attraction on the outer shell decreases. The effective nuclear force of attraction on the outer shell decreases. So understand, between the nucleus and the outermost shell, if the number of shells or the number of electrons are increasing, then the resultant nuclear force of attraction that falls on the outermost shell decreases. When there is no nuclear force of attraction, no great nuclear force of attraction on the outermost shell, then the outermost shell relaxes because there is no force of attraction. No great force of attraction. Then the outermost shell relaxes. When it's relaxing, you can kick the electron with lesser energy, kick out. You must understand it, right? So I say nuclear force of attraction on the outermost shell decreases. It decreases. And remember, its shell decreases, thus. You must understand ionization potential. When someone is relaxing, it would be easy for you to remove the electron. So the ionization potential decreases. It will be easy for you to remove the electron. So what I'm telling basically is ionization potential is inversely proportional to the shielding effect. You must understand. Ionization potential is inversely proportional to the shielding effect. You must understand that. Now, what is shielding effect? I define. If someone is asking what is shielding effect? What is shielding effect? Will you write all this story? No, absolutely. Don't write all this. You simply write, if in between a nucleus and the outermost shell, if the number of shells increase, then the nuclear force of attraction, the resultant nuclear force of attraction on the outermost shell decreases. Then the outermost shell relaxes. When it relaxes, I think the ionization potential will be lesser because when it's relaxing, it's easy for you to kick the electron out. So one of the major factors in which the ionization potential is depending upon is shielding effect. That is one part of the story. One part of the story. We didn't answer why the size, the magnitude of increase of size which we see is more on the top and it's not that much at the bottom. This is a general discussion what I'm making. So, one of the major factors that influences size or ionization potential or what? Size is of course what? Shielding effect. And if someone is asking what is shielding effect between nucleus and the outermost shell, if the number of shells increase, then it is effective nuclear force of attraction on the outermost shell decreases. When it decreases, the ionization potential also decreases. So greater is the shielding effect, lesser would be ionization potential. Right? Adding to this, observe carefully. Note, not every shell or the subshell. Note that every shell or the subshell will be shielding the same way. Will be shielding the same way. Remember, right, if you have holes within the shells, I think the nuclear force of attraction will be penetrating through it. If you are shielded well without any direction, if there is a nucleus, you are shielding so well that you are covering the entire radius around the nucleus, then you are a good shielder. In some cases what happens, that these subshells move in particular direction. In 60 degrees you have more shielding. 90 degrees you have more shielding, 120 degrees you have more shielding. So when you say 60, 70, 120 directional, that means the other direction is porous. There is no great shielding there. Understand properly. Understand properly. So basically what I'm referring to is SPGF. These are the subshells. These are the subshells. Right? So if anyone is shielding symmetrically in the sense you're shielding full. Here is a nucleus and you're shielding full, you're not leaving any gaps, then you are a very good shielder. If someone is shielding only in a particular angle, directional, 80 degrees, 60 degrees, 90 degrees, that means you are actually leaving scope for the nucleus force of attraction to go in the other way and add on to what? The outermost shell. And some fellows will have, they are porous. They are porous. They have holes. They have holes. Then I think the nuclear force of attraction penetrates through what? Such fellows and falls on what? The outermost shell. What I'm telling here is basically I'm referring to the trend of shielding effect. The trend of what? The shielding effect. You must understand the trend of what? Shielding effect among the subshells. Now if you look into this S has a better shielding compared to P, compared to D, and compared to what? F. You must understand that is the shielding trend. And this shields really well. It shields really well for the simple reason it is symmetrical around the axis. This is basically, when I say symmetrical, I say it's basically non-directional. Non-directional is what? S orbital. So it's symmetrically distributed around the nucleus. So the nuclear force of attraction has lesser scope to go and add on to what? The outermost shell. Whereas I think this P, D and F, they are all directional orbitals. They are all directional. Right? P, D and F. That means they shield only in certain angles. Right? It is D is double degenerate and F is, it is further degenerate. Right? Eightfold degenerate. This is fourfold. And P orbital is also what? Directional. So what I mean, the symmetrical fellow is basically covering well the nucleus. So the nuclear force of attraction that falls on the outermost shell also will be lesser if the electrons are occupying this subshell. These are all directional. On the top, what we see, this F fellow is basically showing poor shielding. There are two reasons for that. First is it is directional. And basically second, it has basically, you can say, for your understanding, it has pores type. It has pores. So when you have pores, the nuclear force of attraction will penetrate through the pore. So becomes this fellow is basically poor shielding effect. And the electrons occupying F will be shielding the nuclear force of attraction very poorly. You must understand. Same is the case with what? D and P, and this is how the trend is. The best shielder is basically what? S. You must understand. Let us apply this. Let us apply this and check out why the size increase you will see in the group will be greater and not that much greater down the group, right? Let us see. Let us say this. So basically this is the trend, and the reasoning also I have given. This is non-directional. So you cover well. You not only cover in a particular direction, you are covering really well. PDF are all directional, and F has another problem. That is, it has a very peculiar shape is F. Why I call peculiar? Because no one knows the shape of F orbital till date. We say that it has what? Holes. Let us apply all this, taking a group. Let's take the first group and check out. Right? Look into this. Watch carefully here now. Watch carefully here. Watch carefully here. Look into the first group. If I write lithium, its configuration 1s2, 2s1. 1s2, 2s1. And this is, if I say this is the nucleus of lithium, between the nucleus and the outermost shell, this is the outermost shell. Between the nucleus and the outermost shell, you have one shell in between in between one shell. You have one shell, that is the first shell, and I write comma, comma, I have not finished it, comma, electrons in S. Look into this, everything detailedly I am writing it. Between the nucleus and the outermost shell, you have the first shell, comma, the electrons are also in S subshell. In S subshell. Now let me write sodium. Sodium nucleus, and if I can write its configuration 1s2, 2s2, 2p6 and 3s1. Look at this. This nucleus, between the nucleus and the outermost shell, you have two shells. You have two shells. That is, two shells is number 1 and 2. 1 and 2. This is one shell. The number is a shell. The number is a shell. Number combined with SPDF is a subshell. So, between this nucleus and the outermost shell, you have two shells, that is 1 and 2, comma, I have not finished, comma, comma. The electrons occupy S comma P. Here they only occupy S. Here they are occupying S comma P. These two are S and that is P. S comma P. If I write potassium, then it is, here is the nucleus of it. This is 1s2, 2s2, 2p6, 3s2, 3p6 and 4s1. And between the nucleus and this outermost shell, you have three shells, 1, 2 and 3. So you have three shells, 1, 2 and 3, comma, comma, comma. The electrons in S and P, you can see they are occupying S and what? P. There is no D here, right? And if that is the case, down the group, for even rubidium and cesium, now what happens between the nucleus, I am not writing the configuration, I am writing the configuration. Now you can understand. Between the nucleus and the outer shell, right? Number of shells increase, no doubt. Number of shells increase. But, I draw the attention. I draw the attention, please. But, number of shells is here also it is 1, then 2 shells, then it became 3 shells. Here also the number of shells increase. Number of shells increase. But, electrons occupy D comma F. You can ask me, so what? They occupy D comma F. And when there is D comma F, these are bad shielders. They are bad shielders of nuclear force of attraction. They are bad shielders. Recollect. You yourself recollect. Look into the trend. S is greater than P is greater than D is greater than F. These two are bad shielders. And these two are actually good. These two are actually what? Good. And the best is S. So what happens in a group from top to bottom, number of shells increase. When number of shells increases, size increases. There is no dispute in it. There is absolutely no dispute in it. The dispute is only the way the size is increasing on the top is not increasing the same way at the bottom. Because even though the number of shells are increasing, at the bottom, they are occupying D and F subshells. D and F subshells. And D and F are bad shielders. And the nucleus is growing. This is a small nucleus. This has become big. This has become further big. This has become further big. This has become further big. So the nuclear force of attraction is increasing. And the nuclear force of attraction is better shielded on the top of the groups. When you shield, then the outermost shell relaxes. And the size increases because it's relaxing. Because S and P are good shielders. The S and P's are good shielders for the top three. When you go bottom, The nuclear size is increasing, so the force of attraction is also what? Increasing. But when the force of attraction increases, D and F can't shield them. They cannot shield them. You cannot shield. So what happens when you can't shield? Then the force of attraction penetrates through the F. In case of cesium and rubidium, they penetrate through the bad shielders, fall on the outermost shell. When they fall on the outermost shell is pulled inwards. No relaxation. Relaxation you see on the top of the group. But when you come down, that relaxation is missing. Rather, it is pulled slightly inwards. Then the size decreases. Remember, I am not telling size is decreasing in a group. No, your teachers are correct. Top to bottom size increases. But the way it is increasing in the first three elements where you have electrons occupying S and P, that much increase you don't see down the group. Because the electrons are basically entering D and F. And when you enter D and F, the nuclear force of attraction penetrates through D and F because they are bad shielders and they fall on the outermost shell. The question of relaxation, which you see it at the top of the group, basically what? Decreases. And in bottom, rather than relaxation, the outermost shell is slightly, slightly. I'm not telling it's a great decrease. It's basically slightly pulled inwards. That's why I said if you remember the values, you have for lithium, it is 100. For sodium, it is 150. For potassium, it is 221. For rubidium and cesium, if you actually see, it is 221.5. And the last one, 221.52. There is increase. But the way it was increasing on the top, actually that magnitude of increase, you basically don't see down the group, you must understand. So that is the subject point, and this is not restricted to the first group. This is everywhere in the 18 groups, you must understand, right?